So before we get into the actual, your questions here, just want to give you an opportunity. If you haven't looked at the exam breakdown yet, do you have any questions? You have any questions related to what the exam looks like, how it's constructed, what the breakdowns are, that kind of thing? So this exam is going to be, I won't say calculation free because that's not going to be the case, but it is going to be calculation light because really there were only a couple of things that we talked about where a calculator would actually be necessary. And we're talking about energy calculations, heat of formation calculations, calorimetry, heat transfer kinds of calculations. That's pretty much it um, as far as calculations are concerned. And um, that is really only on this part of the exam that deals with thermochemistry. The parts of the exam that deal with Lewis structures and Vesper theory, those aren't going to have calculations associated with them. So you will be allowed use of a calculator, but you will probably not need it for, I would say, probably about 80 to 85% of the exam. There are only a couple of questions where it will actually be useful to you. So if there aren't any questions about kind of the breakdown and kind of the construction here, let's get into what you came here to talk about today. So what questions do you have, whether they're from the practice exam materials that I provided or just otherwise? What are some things that we can talk about that I can help you to get ready for tomorrow? So question was, do we have to do you have to know how to draw the three-dimensional Vesper drawings? The answer there is no. Very similar to the quiz that you took earlier this week. I did not require you to do the 3D drawings there either. I will be asking you for Lewis structures. Now, that being said, if redrawing the Lewis structure in 3 dimensions does help you with the molecular shape component or with understanding the bond angles or anything like that, feel free to draw or redraw in the 3-dimensional shape. That's completely fine, but that is optional. You do not have to do it. Good. Okay, so when it comes to the octet rule, so module 7, there are 3 primary exceptions to the octet rule. And they mostly have to do either with capacity or with formal charge. Now, in terms of capacity, we're talking about something like hydrogen. Hydrogen doesn't follow the octet rule because hydrogen's energy level only holds 2 electrons instead of 8. And so instead of holding 8 electrons and following the octet rule, it holds 2 electrons. It follows what's called the duet rule. Helium would be the same way if helium formed compounds, which we know it doesn't. The other circumstance that you can see is we talked about this: nitrogen containing compounds, phosphorus containing compounds, certain kinds of halogen compounds. They can have odd numbers of electrons. And if I have an odd number of electrons, it's absolutely impossible to get to a full octet because I can't get 8 when I have an odd number. So inevitably something one of the atoms, usually the center atom, ends up having an uneven number of electrons. In the case of nitrogen, it's usually 7 instead of 8. And that's primarily the case that we see, is that we get as close to the octet as we can, and we kind of just leave it there at that. And usually formal charge ends up kind of kicking us out where we want to be, or gets us pretty close to it anyway. The third type of example, the hypo and hypervalent compounds, these are the ones that are directly associated with formal charge. So if I look at sulfur expanding its octet to 12 electrons instead of just simply 8, is driven by formal charge. If sulfur makes 6 bonds, and we do the formal charge, 6 minus the 6 bonds with no lone pairs would give that sulfur a 0 charge overall. So there are certain circumstances where that is kind of okay and favored. And so where we see that primarily are in those third period non-metals and below. So we see it with phosphorus, we see it with sulfur, we see it with some of the bigger halogens like chlorine and bromine and iodine. We can see it to a lesser extent with arsenic and selenium, and that's primarily because we don't see a lot of compounds with those elements to begin with. On the other side, hypovalent, where we have a deficiency, that can also be driven by formal charge as well. Where we see that primarily is when we have things that we usually think of as being metallic behaving covalently instead of ionically. So beryllium, for example. Beryllium we think of as an ionic kind of compound because beryllium is a metal. But with certain kinds of elements, beryllium actually can make covalent compounds instead, and beryllium chloride is an example of this. Well, from a formal charge standpoint, beryllium only has 2 valence electrons. So if it's going to hold formal charge, it only needs to have 2 bonds to do that. That way it gets a formal charge of 0. If I try to force it to an octet, I'm going to end up with at least a charge of -2. And we know that metals don't take on negative charges, they take on positive charges, if anything. So from that standpoint, that would be our expectation. And we see similar things with things like boron and aluminum, where from a formal charge standpoint, we would expect that they make 3 bonds because they have 3 valence electrons. And to go beyond that, to force an octet on it, would be to not only cause it to have formal charge, but to cause it to have formal charges that we wouldn't expect on a metal, primarily a negative charge. So ultimately, it comes down to those arguments. The arguments that we're talking about are formal charge, first and foremost, and capacity. So the duet rule, odd numbers of electrons, those circumstances, we just don't have a capacity for filling the octet because we don't have enough electrons to do so, or we don't have the space to do so in the case of hydrogen. Now, I'll tell you, other than hydrogen, which is kind of a common exception, we're much more likely to see a hypervalent kind of compound because those are the ones that tend to be of higher focus on in homework banks and quizzes and those kinds of things. It's far more likely we're going to see something that has a steric number of 5 or 6. than it is that we're going to get an aluminum compound that is anything but ionic. Other things that we want to talk about, get out of the way. Okay. 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 So are we talking about questions like this one, where we have a reaction of some kind, and then we're told you have this amount of this substance, how much heat does it generate? Okay, yeah, I can. So let's go ahead and look at this problem number 5 from the practice test, because I think that'll go a long way to kind of helping us make some sense of this. So the first question here is a question where I need to make delta H from these reactions for this reaction that we're given. And so the thing that we want to do for this kind of problem is we want to try to recognize where do we have some of these materials, some of these substances already, and where do we not have them? So in this particular circumstance, I can look at C2H4 and say, okay, C2H4 is a reactant, but right now I've got it listed as a product. So I'm going to need to flip around this third equation to get that to match up what I'm trying to find. And if I flip around the equation, I'm going to need to flip around the sign on the delta H as well. So this went from positive 52.3 to now negative 52.3. And I can look at, I'm going to avoid the fluorine here. The reason I'm going to avoid fluorine is because I can see from my bank of equations here, I've got fluorine in multiple spots. And so I'm going to kind of hope that by the time I figure out everything else, fluorine kind of figures itself out along the way. Right? So I move on to CF4. I can see CF4 is a product in this reaction here, and I need it as a product in the target reaction, but I also need 2 CF4s, and right now the reaction's only giving me 1. So I've got to manipulate the equation also. I've got to double everything. So 2 carbons and 4 fluorines make 2 carbon tetrafluorides. And my delta H value is going to be double this negative 680. So negative 1360 kilojoules is going to be our response there. And then finally, I need to look at HF. I see that I have HF here. It's on the right side of the equation, but it's suffering the same problem that the previous one was. I have half as much as I need. So I'm going to need to double everything. So 2H2 and 2F2 make 4HF. And the delta H for that would be double of negative 537. So negative 1074 would be the right number there. So I'm going to add these together now. That's what we would do in Hess's law. And what I should see is that I've got carbons that are going to cancel. I have hydrogens that are going to cancel. Everything else is unaffected. So my final equation is going to be C2H4 in the gas phase. 4 plus 2 gives me 6 fluorines in the gas phase. And I've got 2 carbon tetrafluorides and 4 hydrogen fluorides. My delta H value is going to be the sum of these delta H's that we've constructed through our modifications. So I've got negative 1074, negative 1360, negative 52.3. From a sig fig standpoint, if we're adding, we always go off of the least precise measurement. Least precise measurement is known to the ones place. So even though this 0.3 got added in, it's not going to survive the rounding because it's more precise than our least precise. We get negative 2,486 kilojoules for delta H. So that's part A. Part A was just asking, what is the heat of the reaction? Part B is the part that we were asking about originally, which is what do I do with that information if I am not looking just at the chemical reaction by itself? And so the answer to that is we've got to do just a little tiny sliver of unit canceling, dimensional analysis, stoichiometry, whatever you want to call it. We need to start with what we do know. We have 39.02 grams of fluorine. Our first step, we're going to turn those grams of fluorine into moles. And then our last step will be to turn the moles of fluorine into energy. So where do I get the information for the first conversion? Yeah, I need the periodic table. Periodic table tells me that the molar mass of fluorine is 19.00. 19 times 2 is 38.00 grams of fluorine in every mole. My grams of fluorine cancel. Where do I get the information for the second conversion? Why did we have to do part A before we did this? So my delta H value is my numerator, so negative 2,486 kilojoules. My denominator comes from the balanced chemical equation. Balanced chemical equation says that when 1 mole of ethene reacts with fluorine, with 6 moles of fluorine, we get 2 moles of carbon tetrafluoride and 4 moles of hydrogen fluoride gas, and the whole thing releases 2,486 kilojoules of energy. All that we are doing here is we are just kind of realigning that 2,486 kilojoules to the amount of fluorine that we have. So we don't have 6 moles of fluorine. We have what looks to be just a little bit over 1 mole of fluorine. And so we make that adjustment with this conversion. 39.02 times negative 2,486 divided by 38.00 divided by 6 to 4 significant figures, because we have 4 in pretty much every measurement here. We get negative 425.5 kilojoules. So if we do get hit with a problem like this, if there's the Hess's law component before it, we can solve the Hess's law component separately. But if it's like the quiz that you took over thermochem, where all you had was basically the second part, you had a chemical reaction, and then you took the chemical reaction and converted it, that's how you do it. Turn the grams into moles, and then you use the balanced chemical equation to turn the moles into energy. And you treat it kind of like any other stoichiometry conversion. So in some ways, you can kind of think of this as a different kind of mole to mole conversion that you did in stoichiometry. This number of moles equals this number of energy. Pull it directly from the balanced chemical equation and the heat of reaction that you're getting. Better? Want to do more? Was that? Okay. All right. What should we talk about next? Go ahead. Okay. Yes. Okay, so I think we're talking about there's 2 different things that we're talking about here. They're different. So the practice test doesn't have one of these, so we'll just kind of take that into our own hands here. So the first part of that kind of question involved a heat of reaction kind of heat of formation problem. So if I had a problem like this, where I was asked to determine the heat of combustion from the heats of formation here, what I would have to start with first and foremost is I'd have to have a balanced chemical equation. So since this is a combustion reaction, we are going to make carbon dioxide and water. And if we balance this out, 17 to get the hydrogens, 16 to get the carbons, 32 plus 17 is 49. So 49 halves to get the oxygen. And so how we would set this up is delta H for the reaction is equal to the sum of the heats of formation in the products minus the sum of the heats of formation for the reactants. Now we've been given the heats of formation here. So on the product side, I would have for carbon dioxide 16 times, because I have 16 moles in the balance equation, negative 393.5 kilojoules plus 17 moles of water times negative 285.8 kilojoules. So that would be this part of the ledger. On the other side, on the reactant side, for cetane, it would be 458.3 kilojoules. And I would multiply that by 1 because there's only 1 mole of cetane. And what's the heat of formation for the oxygen? It's not given to us. Why do you suppose it's not given to us? Because it's 0. Remember, by definition, the heat of formation is how much energy is transferred when we make that substance from its elements. If the substance is already an element, then it's not going to require any energy to convert it. And so it's going to be 0. Now, when do we see non-zero values? When we see elements that aren't in their normal states of matter. So if I was looking at oxygen in the liquid phase, that's going to have a heat of formation because it's going to require some energy output to liquefy that oxygen. If I have carbon in the diamond phase, it's going to require some energy input to make that carbon not graphite. But otherwise, you would expect it to be 0. So with that in mind, we've got our pieces here. 16 times negative 393.5 plus 17 times negative 285.8. Add those together, I get negative 11,154.6 kilojoules. And I subtract from that negative 458.3 kilojoules. Subtracting a negative number is the same thing as adding a positive. So plus 458.3 to the original, I get negative 10,696.3 kilojoules. So that is the enthalpy of combustion for 1 mole of cetane. And so that would be its delta H value. Now, to go after the question that you were asking originally, similar to the quiz question, well, it's almost exactly like what Norman's question was. Let's say that I have, instead of a mole of cetane and unlimited oxygen, let's say I only have 83 grams of cetane. Well, if that was the case, the process to convert that to the appropriate amount of energy would be almost identical to the process that we did with the last problem. I would take my cetane, convert it into moles, and then take my moles of cetane and convert it to kilojoules. Just like before, I go to the molar mass. So 12.01 for each oxygen, or excuse me, each carbon, and there are 16. 1.01 for each hydrogen, and there are 34. I get 1 mole at 226.50 grams. That's going to get my grams to cancel. And then from the balanced chemical equation, 1 mole of cetane, since our coefficient here is 1, would let out negative 10,696.3 kilojoules. My moles cancel. So 83 times negative 10,696.3 divided by 226.5. Do 3 significant figures because that's all we have in this mass measurement. I would get negative 3,920 kilojoules, which is still a significant amount of energy, which goes to tell you how energetic that combustion reaction really is. This is basically the equivalent analog of the component of diesel fuel that burns. So, in both cases, in the case of the one that we just saw and the one that we pulled off of the quiz here, or similar to it, in both of those cases, you had to calculate the delta H value first. Understand that you could also just be given that value and asked to only do the second calculation. So if I gave you this problem and said the heat of reaction is negative 10,696.3 kilojoules, you could just take it from that spot as well and go straight into the calculation stage. Go ahead, Tess. Right, on the clear this out here. Okay, number 1 on the free response here. Okay, Yeah, this one was in here almost. I won't say almost intentionally. It was in there intentionally. You had to do this very evaluation in that skill builder when we did the Lewis structure skill builder. I think the only difference was I don't think we did the ion. I think we did uh, NCLS, I think, or maybe I think we put a chlorine instead of the sulfur. Um, Nonetheless, we have to evaluate which of these structures are favored if there is a preference. Anytime that you are asked about, weigh one Lewis structure against another, you need to immediately think about formal charges. Formal charges are what we use to evaluate which structure is better than the other structure. And so, just as a recall here, formal charge is equal to the valence electrons minus the bonds minus the dots. And we're looking for as low as possible. Now we know because this is a charged ion, one of these at least is going to have a -1 charge. But what we're trying to reduce is the number of things that have charges, and we want to make sure that the place that has the negative charge makes the most sense to have the negative charge. So if we take the formal charge here on the structure on the left, here, we would look at this and say, okay, for the nitrogen, I've got 5 valence, I've got 3 bonds, I've got 2 dots, 5 minus 3 minus 2, I've got no formal charge. On this carbon, I've got 4 valence electrons, I've got 4 bonds and no dots, no formal charge here as well. For the sulfur, 6 valence minus 1 bond and 6 dots. Here's where my -1 charge sits. So I've got a negative formal charge on that sulfur. By contrast, if I look at the other structure here, for the nitrogen, 5 valence minus 2 bonds and 4 dots. I have a -1 formal charge on this nitrogen there. Carbon story hasn't changed. 4 valence, 4 bonds, no dots, no charge on it. For the sulfur, 6 valence, 2 bonds, 4 dots, no formal charge on it. So I've got 2 pretty good structures here. Formal charges are very limited. Only one atom has a formal charge, and that formal charge matches the charge of the ion itself. The question is, which one is better? Which one should that negative charge be on? To answer that question the most fully, we're going to want to go to the electronegativity scale. And if I'm comparing nitrogen, the electronegativity is just above 3. With sulfur, with an electronegativity just above 2.5, I would say that the nitrogen has a greater attraction to those electrons than the sulfur does. And as such, it is going to be more able to stabilize that negative charge and hold that -1 formal charge just a little bit better. So of the two options, that is the one that is a little bit better. Now, since we're talking about not that big of a difference in electronegativity, what this actually falls into is what in organic chemistry they would call major structures versus minor structures, where we can talk about resonance as, we've talked about resonance as being completely equal. That double bond is just as likely to be here as it is here. This is an example of where it's not exactly even, but there can be a pretty good argument made for the other one. And so what we get into is what's called a major structure versus a minor structure. The major structure would be the one with the 2 double bonds. That one's more likely because of electronegativity. But we could also see there's probably a little bit of character where we've got a little bit of a triple bond on that nitrogen as well, because that would give nitrogen a 0 formal charge. And the sulfur is also pretty electronegative. It can handle that negative charge also. So not to get things confused, you don't need to get into that kind of an argument if you see something like this tomorrow. But what you do kind of want to focus on is using formal charge as kind of the center of your argument. And so I know when I gave this test question in the past, I was looking more at the argumentation and less at which one you chose. Obviously, if you chose the right one, that's great. But the bulk of the points were on the argumentation. And if you make a solid argument for the left structure, I did not dock you that harshly, because, like I said, you could make a well-reasoned argument for why the left structure is favorable, but it is not the most favorable. All right, other questions, things that we want to go over? Go ahead, Jack. All right. When a 9.9 gram sample of solid sodium nitrate dissolves in 85 grams of water in a coffee cup calorimeter, temperature drops from 22 to 13.2 degrees Celsius. Write a balanced equation for the process. And assuming the specific heat of the solution is the same, calculate delta H. Okay, so a couple of things going on here. Now, first of all, as far as letter A is concerned, probably the easiest thing to do is to overthink what A is asking. We're talking about a solid sample dissolving. Well, that we can describe relatively easy. That's basically it. Now, if you want to go for extra credit and cookie points, you could turn this into the ionic equation just as easily and talk about how the fact that when it actually dissolves, it would ionize because that's what ionic compounds do. I would have accepted either one. So that's part A. And I've talked often about kind of the concept of there are times I put questions in here to kind of see who really knows what they're talking about and who only kind of knows what they're talking about. And that's an example of one of them there. And that's also one of the reasons why you've got that built-in bonus, so that if you don't fully understand the question or you just whiff on it, it doesn't hurt you that bad. You're still very much in the running for doing pretty well. So that was part A. Part B, if the specific heat of the solution is the same as water, calculate delta H. So we have to remember, so what we're doing here is calorimetry. So we're looking at the heat of solution as being equal to M for the solution, C for the solution, and delta T for the solution. Well, we have all of those. We have the mass of the solution. The mass of the solution is, when we combine these two together, 9.90 grams and 85 grams. So 9.9 and 85.0, I get 94.9 grams of solution. So that's what's going right here. Specific heat, we were told 4.184 joules per gram degrees Celsius. And delta T, remember, that's final minus initial. So 13.2 minus 22.0 degrees Celsius. So if I do that calculation, 13.2 minus 22.0, I get negative 8.8 degrees Celsius there. So Q for the solution would be the product of those three numbers, 94.9 times 4.184 times the negative 8.8. And if I do that to two significant figures, because I only have two significant figures after I do this delta T subtraction, I get negative 3,500 joules. Unfortunately, we're not done there, though. Remember, this is a calorimetry experiment. Calorimetry experiments are measuring what's happening in the solution, not the system. The calorimeter and all of its components are always part of the surroundings, not the system. So if I want to know delta H for that reaction, I need to take the opposite of the heat of solution, which means that instead of negative 3,500 joules, we're talking positive 3,500 joules. And since it's not asking for a molar heat value, we can stop right there. If it was asking us for the molar heat of the reaction, we would have to take that 9.9 grams of sodium nitrate, turn it into moles, divide the delta H by the moles to get the molar value. Not asked to do that, not going to do that. Save myself some time. You know as well as I do, every minute and every second of those exams can be very, very well spent or very poorly wasted, depending upon how much we spin our wheels doing things we don't need to do. All right. More questions, other things to talk about? So for sigma and pi, what we are talking about is we're talking about the difference of overlaps. So in sigma bonding, we're talking specifically about the direct overlap of orbitals. And so what kinds of orbitals do experience this kind of direct overlap? Hybrid orbitals, s orbitals, or p orbitals that have this side to side kind of orientation. Remember, direct overlap is the strongest kind of overlap. Sigma bonds exist in all bonding, regardless of whether it's single bond, double bond, triple bond. The first bond any two atoms make is going to be a sigma bond. It's going to be that direct overlap. If multiple bonding comes into play, that's where pi bonds come in. And so if I look at pi bonds, what I'm looking at is instead of that side-to-side overlap, where we've got the orbitals directly on top of each other, in a pi bond, we get them parallel to each other like this. And so you can see there's not as much overlap here because I can't get these orbitals close enough to each other to actually get them to overlap directly. They overlap in parallel instead. So you get a little bit of overlap here, you get a little bit of overlap down there, but primarily they don't touch each other a whole lot. And that's why they're a good bit weaker in terms of their bond strength than the sigmas are. The sigma bonds, again, we're looking at, again, the direct overlap there. And so the distance between the nucleus and the electrons that are being shared is a lot smaller because those atoms are able to get closer to each other through that overlap process. So we tend not to see pi bonding except when we have a double bond or a triple bond. And so that comes directly out of the analysis of the Lewis structures that you are drawing or that you're evaluating. So just coming back to this example, in both of these structures, we ended up having 2 sigma bonds and 2 pi bonds. Sigmas, I've got 1 sigma from the carbon to the sulfur. I've got 1 sigma from the carbon to the nitrogen. And then I've got 2 sets of pi bonds going from the carbon to the exterior atoms. Just depending upon which structure it is, tells us which direction those are going. So structure on the left, you've got both sets of pi bonds heading toward the nitrogen. Structure on the right, you've got a pi bond going to the sulfur and a pi bond going to the nitrogen. You've got 1 in each direction. Next. Yes. 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 So a triple bond would have a sigma bond and 2 pi bonds. Together, that would give you the 3 bonds. A double bond would have a sigma bond and a pi bond. that would give you the two bonds that make up the double bond. In terms of the carbon is going to be sp hybrid either way, because it needs to make two pi bonds regardless of which structure it makes. It's just a matter of what direction those pi bonds are pointing. Further questions? Okay. So the next one after this? No? Okay. All right, which of the following would we expect to be flat? So we're looking for some kind of a planar structure here. So what we have to think about is, in examples A, B, and C, what are the steric numbers? So in A, what's the steric number for molecule A? It's going to be 6. And so if two of those are lone pairs, we put them opposite each other, all that would be left would be the square planar shape. So a planar shape is two-dimensional. It's flat. So A would be flat. All right, what about B? What's the steric number on B? It's 5. 5 is trigonal bipyramidal. There's only one subshape of trigonal bipyramidal that is two-dimensional. It's the linear shape. I need 3 lone pairs for linear. I don't have that in this case. What I've got there is seesaw. Seesaw is definitely not two-dimensional. It's three-dimensional. You've got pieces that are coming forward and backward in addition to up and down. What about C? Steric number is 5 again. So again, we're talking trigonal bipyramidal. Trigonal bipyramidal is not a two-dimensional shape. It's very much three-dimensional. It's got the two different planes, the axial and the equatorial. So the only one that is flat would be the first one, the one that's giving us a square planar. Now, what other shapes could we say are flat? Linear. Either of the bent shapes, whether the trigonal planar bent or the tetrahedral bent. Once we get down to just those three atoms, it's two-dimensional. Trigonal planar, square planar, and that's about it. I guess T-shape. T-shape, you can make an argument for that one as well. So that's where you want to leverage that equation sheet and that Vesper table that you had on the quiz. So try to use that to help you visualize what these kinds of things look like. And if it's involving those more complex shapes, use that to help you figure out, okay, if I have this configuration, steric number 6, 4 bonds, 2 lone pairs, that's square planar. If it's got planar in the name, we know it's flat. It's two-dimensional. All right, more questions. Right, any questions from Zoom? Okay, thank you for responding. Right, if there's nothing else, we can call it a day right now. So give you another chance to ask. All right, so um, just as you're kind of thinking about things, you know this is now the third exam that you've taken with me. You also know that I wrote most of the chapter quizzes that you've taken thus far as well. You have an idea of what my style is. Yet make sure that you're practicing what you need to do. You can't help yourself tonight by just reading through your notes and going through the slides and reviewing stuff kind of passively. The way to study for these exams is to do what it is that you've been doing all along. So, work on drawing, work on, get into, active, get into top hat, start looking at those extra practice problems and seeing if you can figure out some stuff. That's how you're going to get to the spot where you know what you're doing and you can improve and you can actually get real practice on these ideas. You've also got all the quizzes. Those quizzes are valuable because usually on the quiz, I'm pulling stuff that I think is the most important stuff out of those modules. So between that and the practice exams and all of that stuff, that's where your heavy focus needs to be. The time for reading the book and going over your notes was when you were doing your assignments, not at this stage. That stuff should be just reference material now. I forgot how to do this. Let me go back and figure out how to do this. So use your tools, and if you do have any questions, something comes up and you're like, gee, I don't remember how to do that, or I need a reference, reach out to me. Send me a text and say, hey, can you point me in the right direction here? I'm happy to do it. Now, text at 2 in the morning, I won't be happy to do it because I won't be available to answer it. But if it's within a reasonable hour, like before 11, you're gonna probably find me awake, and I'm more than willing to help you. So if there are no further questions, I'll close out the study session here and let you get to studying on your own. I'll see you tomorrow.